Yeah.
Yep.
Great. So let me just begin with a little recovery from the last week. You remember we struggled with the question about the heart rate.
Yeah.
And there was this request. Yeah. I'm gonna put it in here for you. So this was the question. And yep. So use the progression of this average heart rate seconds to make a graphic prediction of the instantaneous heart rate at 30 seconds. Is the atlas heart rate less than 65 beats per minute at 30 seconds? Estimate the heart rate at 60 seconds. Well, but there are quite few operations that we need to make here. But first of all, let's determine what of the progression of heart rate seconds in here. So you remember we had such a certain table, there was like time step of 10 seconds, right? And certain heartbeats values at this moment of time. So we can recall that the curve was exponential for us because the heart rate was constantly growing due to the fact that person was exercising, right? And seconds of this exponential line, it's actually coming from the geometry of a circle. Second in a circle is such a line that connects 2 points of this circle. So seconds of a graph, it's basically some straight line that connects 2 points of our graph together. So let's assume we have certain value of heartbeats at point of time 10 seconds, and we have some number of heartbeats at point of 20 seconds, okay? And the second between these 2 points is going to be a straight line that connects both of them. In the same way, if we have a point that starts at 0, 0, and we would like to make a second between this line and point of 20 seconds, it's going to be the line that connects these 2 points. If we make the same second representation with single line, let's say we are going to pick this point when we have time equals 10 seconds. And just the number of heartbeats is here. Let's assume our reference point is 10 seconds, right? We can create series of seconds. We can join 10 seconds with 20 seconds. Then later on, we can join, we can create a second connecting this point, which is 10 seconds, and point on 30 seconds. And we can keep creating numerous amount of such seconds, right? You can see that because we have infinite amount of points on this curve.
Yeah.
But in this example, I showed you how we're moving farther away from the initial point. But let's assume we're moving the other way around. We're moving closer to our reference point. Then you can see that the slope of a line created in such way is going to decrease for this particular case, and it's going to get closer and closer to the tangent line in a point. The closer we take this point, the more accurate would be approximation of a tangent line at this point. And this is actually what they're asking you to do. Use the progression of this average heart rate seconds to make a graphical prediction of instantaneous heart rate at 30 seconds. So there, we had some values. Let's say there was 50 heartbeats at point of 40 seconds. There was 60 heartbeats at point of time of 50 seconds. And this line joining these 2 values together with the reference point. So the reference point is 10 seconds and this is the second point in time. Basically coordinates 50 and 40, where 50 is a x coordinate variable, and 40, oh yeah, sorry, I said it was the other way around. So 50 is the number of heartbeats and 40 is the number of seconds. So when you join these 2 points together, you are getting an average rate of change of this slope in this interval, because we are taking values starting at 10 seconds, and let's say our second reference point would be at 30 seconds. And that's how you get a value of an average rate of change it over a certain period of time. Basically, the seconds are giving you this average rate of change. Do you get my idea?
Yeah.
Yep.
So what this question asks, use the progression of this average heart rate seconds to make a graphical prediction of the instantaneous heart rate at time 30. To make a prediction of the instantaneous heart rate at time 30, we would have to make multiple of seconds that has reference point of 30 and link it with other points on our curve, like we did to point that starts at 10. But in this case, we're looking at point that starts at 30. So we would keep approximating it, keep creating seconds until we are reaching some value that is extremely close to the second value. If we choose points from both sides of the reference points, we are going to approximate it from both directions. From one side, you can see that the angle changes towards here, and if we join these 2 lines that are lower and lower and lower, they're going to approach this point from the other side. So basically, this is an idea of that, how we can scale our seconds up to the point when second is can be equivalent to the slope of a tangent line in the point. The greater the approximation, the smaller value we're taking between these 2 points, the closer would be the approximation. For an instance, you can take two different points, the one that is before the second value and the one that is after. Let me clean up it a little bit because it's kind of messy right now. Let's say our reference point is 30 seconds here, and we can take point before, we can take a point after, let's say here. And if we make a line through these 2 points and through these 2 points, we're gonna see that our tangent line lies somewhere between these 2 seconds that we created, you see? And in rough approximation, we can say that value for the slope in this point somewhere between 2 values, but we're going to look at examples where we are looking for exact value. So for now, we remember what seconds are because we're going to use them a lot. And also we get familiarized with how are we approximating the slope of a tangent line. But before we are going to jump into practical solving of such examples, I would like to make sure that you guys are familiar with rationalization of radical expressions. Have you done that before?
Radical expression. I think so, yeah.
So let's just take a look at the outcomes of today's class. So this is just the topics we're going to cover today. First of all, we're going to take a look at the methods of rationalizing radical expressions. We're going to rationalize radical expression in the numerator and denominator. And by the end of this class, you will be able to approximate the slope of a tangent line at a specific given point using the limits function. And in terms of seconds, you also will be able to explain it. So, and finally, you're going to get familiar with physical interpretation of rate of change. I believe Yusuf must be happy about it. We're going to talk about physics a little bit today. Yep. And also we're going to describe rate of change in terms of limits as well. So let's take a look at the radical expression and how we can rationalize them. So we know that there are basically two types of radical expressions that we can see. One of them is when we have one term. Here you can see that it's simply some product of 4 times root out of 5, and two terms expressions where we have sum or difference of two radicals. You got this idea, right?
Mhm.
There are maybe more than two radicals. There might be a third one. There may be multiple of them, and each one of them requires specific approach to rationalize it. The reason why we would like to learn how to rationalize the denominator is because it's always better to divide by the integer rather than radical. And it's pretty intuitively understandable, right? Because it's always better to split up into even parts, even portions. And it's always easier for the PC to calculate such an operation because we are getting rid of the root operation. We're getting rid of product operation. It's simplifying everything for us drastically. And it's important for a computer because every operation takes time to process, right? So we want to make it as simple as possible. General idea of how to rationalize such an expression is that when we have one term radical, we simply need to multiply both numerator and denominator by the sorry when we have one term expression, we need to create a square root out of it to get rid of the radical expression. If we can square up root out of 5, it's going to be 5. Make sense?
Mhm.
One of the easiest way to do it is simply multiply numerator and denominator by the same coefficient to maintain the initial equation. This just like subtracting or adding to the both sides of the equation. It's the same one with the multiplying and dividing. So for this example, we're simply going to multiply both parts by root of 5. And as the result, we're gonna get 3 times root of 5 divided by 4 times 5, because can you see this without additional explanation why it's so?
Mhm. Yeah.
Because otherwise we won't spend much time on this. Can you guys give me example how would you transform this two-term expression?
Would you, for this one, would you add it? Add the first. So you would add root 6 plus root 3 to the top and bottom. So you'd write Can I write it?
I can write it. So I would add, or like I would multiply.
Add.
I would add.
So if you do a plus side at the end, no, at the end, like
Okay.
a separate,
Like
yeah,
like this.
yeah, and then you would do √6 plus √3 subtract, no, divided by √6 plus √3. Would that work, or does?
So we would refer to principle the same one as with the one term when we want to square up the radical, right? When we're squaring up the radical expression, it automatically converts into integer because any square, any root function times square to the power of 2 is going to be equal to a plus or minus a, basically.
Okay.
Oh no, sorry guys, it's going to equal a, just equal a. And here we also want to transform square root of 6 and square root of 3. And one convenient formula that we should remember here is the difference of squares. Remember, a square minus b square equals a minus b times a plus b. You remember this?
Yeah.
So basically, yeah, that's what we want to see on the bottom side in the denominator in order to convert a to the a square. So instead of adding up this product, this term, we're just going to multiply by this term, but we're going to multiply not simply by this term, but by its conjugate. Let's, I'm just gonna show you this final example. Here we're going to multiply it by √6 minus root of 3, right? Because that's how we're going to create this pair that we're looking for. After multiplication, we can see that on top is going to be 2 times root of 6 and root of 3 divided by √6 plus root of 3 times √6 minus root of 3. And you can easily see that this is the difference of a square function, right? And when we combine it, we can see that in the denominator, we're going to have 6 minus 3, which is also equal to 3. And that's how we simplify it. We're clear with this one?
Yeah, I got it.
Can I ask, how is the √6 plus √3 a difference of squares if it's a plus?
I'm in this example, look, the formula for difference of squares, it looks like this. First bracket has plus or minus, and second has plus. But it doesn't really matter to us whether there is a plus in first bracket or in the second, because if we change position of the multipliers, product doesn't change, right? So it could be plus in the first bracket or it could be plus in the second bracket. But we should have two identical brackets with similar terms, but opposite operations between them. In the next slide, you're going to see this pair of numbers where a minus b and a plus b is two conjugate numbers. And in this example, initially we had sum. Imagine this as a bracket with the sum in it. And we need to find the second bracket that has same terms, but different sign between them.
Okay.
And such bracket would be square root of 6 minus square root of 3.
Okay.
In the next slide, here is the formula, basically algorithm. Remember it or write it down, and it would be perfect. So when the denominator of a radical fraction is a two-term expression, you can rationalize the denominator by multiplying it by the conjugate, and conjugate is such a pair of numbers or a bracket or a combination that has same terms but different mathematical operation in between them.
That's what I was trying to do before.
This is what you were trying to do?
Yeah, when I
Oh, yeah, and you said add, you mean
yeah,
add like this. Okay. But here you see the sign is crucial. You gotta pay attention to the sign in the brackets.
Mhm.
So you got this?
Yeah.
Perfect. Let's move on. Here are some examples. So Yusuf, Alan,
Yeah.
wherever you wish, choose 1, 2, or 3 for yourself and try to solve it. I'm going to pick the last one. Which one do you prefer?
The second one.
Second one, okay. This is for Alan, right? And Yusuf, first or the last one?
I'll do the last one.
Okay. And I will do the first one.
Okay.
Can you draw on the screen?
Yeah.
Perfect. Then add your solution as soon as you finish.
Okay.
So here we're simplifying the denominator. The denominator is the one on the bottom.
Yeah.
So here, do you get an idea why we're multiplying both numerator and the denominator?
Yeah.
Because if we are multiplying in this way, simply we're multiplying by 1, because this bracket is equal to 1. So, Yusuf, you finished?
Yeah.
So this is, can you explain what you written here?
So I just to find the reciprocal of it, I just switch the numerator with the denominator,
Uh,
and it'll be 2/7 minus 3. 7 squared. Square root 7 minus square root 3.
okay, but what you did, you found the conjugate to the whole bracket, basically.
Yeah. Yeah.
But now we are trying to simplify either the denominator or the nominator. So we're trying to simplify one of two parts of this expression. Top part is the
Simplify
nominator.
it.
Yeah, we're simply trying to get rid of the radicals in it.
Oh, okay. I can simplify it.
Sorry if I wasn't accurate with the task.
It's okay. It's very hard writing with this.
Yeah, I can understand it. Alan, are you with us?
Yeah, I'm just doing the paper right now.
Okay. Okay.
Yeah, I think I'm gonna write this down. I don't know if it's fully right, but
You can tell me, I can help you write it down. You just read what you have on your paper.
I have 5. The equation, well, yeah, 5 over 2 square root of 6, yeah, plus 3
Yeah,
times
okay.
2 root 6 subtract 3 divided by
2 root 6, subtracted 3, yeah. Divided by 2 root 6.
subtract 3.
Okay,
5 and then a bracket,
okay,
2 root 6 subtract 3
yeah,
divided by bracket 2 root 6 squared
okay,
subtract 3,
okay.
and then that equals, I did 10 root 6 subtract 15
Uh,
for the top, and then 20.
sorry, Alan. From
Mhm.
this stage, what you've done, you multiply the numerator by this multiplier and denominator by this. And
Yeah.
now you're combining it into the difference of square, right?
Mhm.
So at this stage, we should have something like this. These both A and B are squared.
Okay,
I believe you had something different here.
yeah, I didn't square the 3.
Yeah. So yeah, and after this, if in this example you're trying to rationalize the denominator, so we leave numerator as it is, and
And then
if we can simplify it even more, if we can like extract something from the brackets, it's even better. But in this case, we can't. So, and we're just simplifying the denominator even further.
would you square the 2 and then it'd be 4 times 6
Yes, exactly. It would be 4 times 6.
and then subtract 9.
Yeah.
So we final answer would be 5 bracket 2 root 6 subtract 3
Yep.
over 24 subtract 9, which is 15.
Yep. But still, is that the final answer?
Can you if you could simplify the top, then no, but I don't think you can, so yes.
In this case, you can divide by common fracture. For example, 5 and 15, they have greatest common factor of 5. So you can divide 15 by 5 and basically 5 divided by 5.
Okay,
That's the way of simplifying, because 15 can be represented as 3 times 5, and that's where you subtracting this 5.
yeah,
Can you see it?
I can see that.
And this would be the right way to simplify any expression that you see later on. Make the denominator as simple as possible.
So it'd be 2 root 6 divided by 3, and
Uh,
subtract 3 divided by 3.
yeah, 2 root 6 minus 3 divided by 3. And Yusuf, yeah,
Yeah.
you got it right, what I can see. But um you mistaken 7 with 2, right? Now you're
No,
assuming
it's
2.
it's supposed to be a 2, but it's just the writing thing wrote it 7.
Yeah, but so you got the idea right. You're multiplying by accurate conjugate, but in initial expression was a little bit other way around. You see,
Yeah,
the nominator is on top, but it doesn't matter. The most important for me stuff right now that you got an idea of how to simplify it.
yeah,
If you see it later on. So here you multiplying, it would be 2 minus 3. Yeah, exactly. Great. Perfect. You can leave it like that.
yeah, and then just like divide and then just solve it.
Yeah,
Divide it, so then it would be like, this is the last step here. So then it would be -2. Like that.
yeah, perfect. So you completely simplified the expression.
Yep.
So let's just save it a little bit like this. I'm gonna save it to the file. Great. I'm gonna clear up the notes now.
Okay.
And let's move to the next slide. Here you can see the maybe basically conclusion of the idea, how we are working with one term expression and how would we work with two-term expression. And so screenshot it, save it for yourself, and you're also gonna have this in your hard copy material and in the lecture material from this class. So just keep in mind that this table can help you to identify which approach to use in particular situation. Important thing to remember, if we have only the radical, if we have this type of representation of the denominator where we have the integer times radical, when we can get such a representation, guys? When we're dividing something and we have a residue, right? When we have a remainder, it can be represented as decimal places, because this is what it is. And if you want to simplify it, you're simply multiplying it by the radical. You see, no need to carry on this coefficient that is an integer already. You're simply substituting the radical into integer
Mhm.
by this method.
Okay.
Perfect. Let's
Are we-
make it. You have
Okay.
any question? Yeah.
Are we on unit 1 or is this just touching up on?
This is first unit. It's introduction into calculus. The reason why we're covering up radical, sorry. The reason why we're looking into ways how to simplify radical expressions, because when we work with the graphs and we work with seconds, as you've seen before, we are working with the fracture of a curve. And this fracture of a curve can have any value. It can take any values. In most practically, these values are not going to be in integers. And you need to know how to transform them in case if you have weird denominator or weird nominator.
Mhm.
This is going to be useful in practical tasks.
Yeah.
But because for an instance, you may not have a integer fracture of time, and let's say we are not measuring the scale by seconds, like 1 second, 2 seconds. Imagine if we would have a scale of root of 2, so the second one would be 2 root of 2. just for an instance. And you remember the equation for the slope? It's run over race, or race over run.
Pressure run, yeah.
It would be change in a y direction or change in x direction. And here you can see that the formula that you're eventually going to get for the slope, it's going to be, let's say, it's going to be 1 and 2 values. So it's y2 minus y1 equation of a slope. So it's going to be 2 minus 1. But for the variable that we are looking into, we're going to see that variable taking these values. So we're going to have 2 times square root of 2 minus square root of 2, right? And how would you solve this? Tell me. You would just say 1 by square root of 2? No, you still would need to simplify it, get rid of the radicals in the denominator, and you're going to see that the result is going to be square root of 2 divided by 2.
Mm-hmm.
And in tables, for example, math tables with some sinus values or cosinus values, did you mention that they usually have integer in the denominator rather than fracture or radical? There are, if I remember right, have you studied trigonometry?
Yeah.
Yeah.
So there is a value for cosine of I believe it's 45. It would
Yeah.
be square root of 3 divided by 2.
Yeah, or something like that. I think it's square root or 1 over square root of 2, or other way around.
Square root of so 1 over square root of 2, and still 1 over square root of 2. You see, it can be represented with an integer denominator.
Yeah.
You're gonna see why it's helpful when we get to the examples. So we are clear with the ways of rationalizing the expressions with radicals.
Yeah.
Let's make a few more exercises.
Okay.
Conjugate, it must be easy. You can say it without writing. What is the conjugate to D, Alan?
Well, is this all over 1?
Yeah, but we're looking for the conjugate, and we don't care what is in the denominator for this one when
Yeah.
we're looking for the conjugate.
Uh,
Conjugate, we're looking for
So-
single line.
So 3 root 3 subtract root 2
Yeah, that would be the conjugate.
over. Is it still over the same thing?
In this case,
Mhm.
look, when we were simplifying the previous examples, we had this radical expression in the denominator, right? I can, where is it? Okay, wherever. The radical expression was in the denominator, but here the radical expression is by itself. You see? No matter where the radical expression is, to simplify it, we are looking for the conjugate to the radical expression, not to the whole expression where we divide something, or radical expression over something, or there. You got my idea.
Yeah.
We are simply looking for the conjugate to the radical expression as it is. And you already said the right answer. The conjugate to this one would have the same terms, but it would have opposite sign in the middle. And did you get an idea why conjugate? Because it allows us to represent these values as a power of 2. And the power of 2 of square root is an integer.
Mhm.
That's what we are looking for. That's why the conjugate. So Yusuf, what about the conjugate for the second one, for f?
For F,
So imagine, I'm gonna give you a hint how to work with it.
yeah,
Imagine you have only A, you see letter A
yeah,
underscore plus some letter B. And you need to find conjugate to this. And then to find conjugate to this would be square of A minus root of B. That would be the conjugate to the one to the left hand side. And in this case, to find the conjugate for this example, the way I like to do it, I just subtract this value like it's square root of A. And this value is just going to be root of B, right?
yeah,
If we subtract them, we can see that only things that needs to be changed is the symbol. But for me, in this case, you see we have minus here. If we swap them with one another, it wouldn't change the result of this operation, right?
yeah,
But we're gonna have more convenient representation where no one has a minus in front of the coefficient. We have minus between the operations here. Is this equivalent to the one on the left hand side? This one, is it equivalent?
yeah.
So, and what would be the conjugate to this?
So then the conjugate would be,
You see, this works both ways.
just both ways, yeah.
This one conjugate to the one on left, and one on left is conjugate to the one on right. And only difference is the sign.
Oh, okay, so just when the sign is different. This is like the other one that we did before, right?
Yeah. So basically, what would we multiply by to get a difference of squares?
So it would be two square root 2 plus square root 5.
Yep. And the product of this would be
Product of this would be 1 second.
you shouldn't say the final answer, just say the middle step. How would we write it?
Then just like simplify, just like do the, yeah,
So next step, we can skip this step if you can do it in your head. So 2 times square root of 2
yeah,
taken to the second power is pretty easy. It's 2 times 2
8,
plus square root of 2 times square root of 2. So it's going to be 2 times 2 times square root of 2 times square root of 2, right? Because we are applying this exponent to both of this.
yeah,
And it's going to be 4 times 2, it's going to be 8.
8, yeah,
You can make it in your head, or if you are not willing to skip this step, you write like this, then minus, because we are looking at the difference of squares, minus square root of 5 square. But would it work if let's say, can we make this something like that if both brackets are going to have the same sign in it? Would it work? Can we transform it somehow?
yeah.
You would open the brackets, you
Would
would
open the
multiply
brackets.
them between each other, but you
Yeah.
still won't get rid of the root in here. And you can, if you make this operation, you can see that you're going to multiply square root of 2 by square root of 5, and it's going to be square root of 10. It's really,
Yeah.
it doesn't really work as a it doesn't really simplifies it. This would be the simplest representation. But if you have plus here, beautiful, we can fold it. Basically, what we're doing it, we are folding it together into the other form of a square minus b square. You got an idea?
Yeah. Yeah.
Perfect. Let's
Like
move.
folding it together. Yeah.
Like we're looking for the second part of something unified, or what would you call it? We're looking for second part of a puzzle in this way. And there are many ways to rationalize other equations like this by looking it for parts of what we really need, because you remember there is a formula for product for the sum of square of cubes, for example. There is another formula for the difference of cubes, and there are multiple factorizations of these expressions. And if you know them, like a multiplication table, if you know these operations like by heart, it's going to be easy for you to see this similarities and differences in the equation you're working on. You see what I mean? Basically, after you learn the alphabet, it's much easier to make words. Remember the basically what we covered in the first class. So let's move on from this point. The second exercise, I'm gonna show you how to solve it efficiently. Rationalize the denominator of each expression. So denominator, we remember it's on bottom. So in this case, we don't care how the numerator actually looks like. So we're looking into ways, trying to actually choose the approach to simplify denominator in this case. And we can see here that we have this, remember me, how is this type of expression called?
Reciprocal?
Almost. When we have a square root.
I don't remember.
You see how, and we just covering this. Look,
Good.
it's radical expressions. And this is only the simplest part of what we're going to look into. So yeah, this one, right?
Yeah.
Here I can see that I have radical of square root of 2, and I only need to simplify it. So I choose to multiply both numerator and denominator by square root of 2. Here I can see that the numerator is not going to change a lot. I'm not even gonna add brackets because there is something we can simplify here. You see, here is 2 square roots. They're combining into integer, right? These 2 square roots are going to combine into the square root, unfortunately. The math under the square roots works in the same way. So we're going to multiply 3 by 2. So square root of 3 times square root of 2 is equal to square root of 6. And on the bottom, we have, again, square of a square root. It's equal to 2. And I'm going to move to the next line. Basically, what we can see here, we have 2 times square root of 6 minus 3 times 2 divided by 2, right? And we can simplify it even further by factorizing 2 on the top. We make this brackets. Oh, sorry. So You see, we're
Yeah.
factorizing 2, bumps, and easy. This is the representation, the final one. For the second example, again, here we're going to multiply it by square root of 2 because we only need to get rid of the radical expression. It would be done in exactly the same way, and we would simplify it as we did previously by factorizing denominator and denominator. Let's move the third exercise. Here we're going to rationalize the denominators. So this is example of two-term expression, right? And when we're working with two-term expression, we remember that we need to find the conjugate to what we're trying to simplify. And here we are trying to simplify the denominator. And the conjugate to this one would be, can you tell me?
Root 3 subtract root 2.
Yeah. So you got it. It's pretty easy for you now. And
And then it would
see, it's gonna be 3 minus 2, so 1 on the bottom, and just square root of 3 minus square root of 2, 2 times.
Yeah.
Yeah. The second power. See here in this example, exactly the same way. And the conjugate would be 5 square root of 2 minus square root of 3. That must be pretty much clear now, right?
Yeah.
So the fourth exercise, numerator. I don't know why would we have to explain this again, because it's pretty much the same, right? We're still multiplying by the same multiplier on the top and on the bottom. We're just simplifying the numerator now.
Okay.
So what would be the conjugate to this one?
Would be root 5 plus root 5 plus 1.
Yeah, and to this one?
Root 5 subtract 2.
Great.
Okay.
Oh, this one. This is what you are going to see a lot in solving equations at school, maybe even at job, because basically what you see here, it's an operation with a variable, right? Variable that can take some values. And you need to know that they can be simplified in pretty much the same way. How would you simplify this one if we need to simplify the numerator?
Root a plus root 2.
Okay, and this one?
Root x plus h plus x.
Yes. So you see that this part is basically A and this part is B. So we can group them up to see the easiest solution. And I'm gonna write it down. Let me see. Can you simplify this for me? I'm gonna write it down right now. It's gonna be x plus h minus x squared divided by
X
plus h minus plus x, right? Times x.
Yeah.
Do you think we can we simplify this or write it in the other way around? Maybe as as product of two elements, so factorize it.
Can we subtract the x and remove the squared?
So we can here we definitely need to subtract x, you see, because we have it as a multiplier in the denominator, and we can see that we
cancel out the x and remove the squared off the x squared.
yeah. So we're going to basically what you can see here, because x divided by this denominator plus h divided by this denominator plus x squared minus x squared divided by this denominator, right?
Hmm.
You know, you see why?
Yeah.
Because we can represent this as a product of different factors, fractures, or fracture of x, fracture of h, and fracture of x squared. And everywhere we have x. So we're going to simplify it here. We're going to subtract it here. We're going to keep it here because we can't subtract anything.
Yeah.
So yeah, I'm just want to make clear you see this as a part of something unified. You can if you can break something unified into parts, that's what important. So I hope we're clear with the radical expressions. And let's talk about the slope of a tangent line. So we already identified it. What is a tangent line, right? That is perpendicular to the curve at certain point. But we struggled with defining tangent line at a point, right? So here you can see that this is what we talked about when we creating sequence of seconds. Can you see this drawing on the bottom?
Yeah.
We have a sequence of seconds that are defined by initial point P, the reference point, for example, the one that we are interested in, right? And it's defined by point Q. And this point Q is pretty much what we are looking into. You remember, you said, how can I find the second point for the tangent line if it is outside of the curve? We can't. So the answer is we can't take a point that is not lying on the curve, right? We are restricted to the domain of a function. So we need to pick such point Q on the curve that is on the curve and that is as close to the P as possible. So because we already determined that the closer we get to this point P, the more accurate would be the value of a tangent, of a slope of a tangent line in a particular point. So here we can represent coordinates for this Q as x plus some value h. And I'm going to explain you what this value is. And function, initial function, dependent on x plus h. Basically, this is equal to y, right? But this would be the value of y in point Q, and this would be the value of x in point Q. You got it?
Yeah.
So, and what is this h exactly? Why we're doing it like this? Because y is the dependent variable, oh, right? And x is independent variable. Or is it the other way around? Can you tell me?
It's the independent variable.
Pardon?
It's the independent variable.
So x is an independent variable, right?
Yeah.
So we can adjust x as much as we wish. So we can take value of x farther or closer, and most likely it's going to be related to the curve we're studying. It's going to be in the domain because that's how domain is defined, right? We're taking different values of x and projecting them on a discrete two-dimensional surface. So in this case, we're going to change x as well, and f, our function, is going to change depending on the x value. And how would we change the x to satisfy what we are looking for? We are looking for the most accurate representation of a slope of a tangent line to the point. We would change this x coordinate as slightly as possible. On this graph, you can see h here. This would be the h, the distance basically from the x1 to x2, where x2 equals x1 plus h. And this is exactly what we see here. This is xq or x2. You can call it whatever you want. It's just some other point that differs from the reference point by h. You got my idea?
Yeah.
So now, knowing this, we would just memorize this, guys. Please write it down on your paper. This coordinates for P and coordinates for Q. How do we represent those? Can I clear it?
Yeah.
Alan, okay.
I'm just writing it down right now.
What?
I'm just writing it down.
Okay, take your time. Please take attention to this drawing that shows that tangent line could look both ways, you see? Basically, it could be tangent this way, or it could be looking this way.
I got it.
It's going to be tangent.
Okay, I just finished writing it down.
And can you tell me the definition of the slope?
Rise over run.
No. How do you understand it in words? What is the slope?
Oh. The rate at which it's increasing or decreasing.
No, not exactly.
Hmm.
I would say that slope is how steep the graph is at the point of tangency. You see, this is right here. So slope gives us the angle of the graph at particular point. How it is related to x-axis, basically.
Mhm.
How steep is the graph? How fast is it growing? How slowly is it growing? This is all the information that slope can give us. So let's move on, and here's some more definition. So this is what I said. Function y can be represented as fx, and we have some point P with coordinates x and y. We can call them x1 and y1 if you wish so. We have some other point Q with coordinates xq and yq. And we are trying to direct this Q as close as possible to the P. So basically what we're imagining it, that P is fixed on the curve. Let's imagine this is the curve, you see? P is going to be fixed value. And Q is going to move like on the rails. It's going to follow this curve. You see, it's like a, I don't know, Six Flags roller coaster. Fixed, it's fixed to the domain. Slope of a tangent. The slope of the tangent to a curve at a point P is the limiting slope of the second PQ as the point Q slides along the curve towards P. In other words, the slope of the tangent is said to be the limit of the slope of the second as Q approaches P along the curve. So we're seeking to limit the value of Q as close as possible to P. You got it?
Yeah.
We will illustrate this idea by finding the slope of the tangent to the parabola. Well, you know what a parabola is?
Yep.
So we have an equation of y equals x squared. And just give me a second. I'm gonna find some reference what we would like to know here. So at first, let's find few points. And we're gonna see why we want to, or do you really need me to explain you why we are limiting value for the second point? Why do we approach this point to the middle? Because you said you did it with another teacher. You approximated using the smaller value or neat close value like 0.001, right?
Yeah.
You already did it and you saw the how it is related, right? You saw that every time you getting closer and closer to the point, the coefficient doesn't change drastically. It begins to change by a fracture, by a decimal, by a 1 tau, fracture of a tau, right?
I'm trying to find the maximum and minimum of that. That's what we're trying to find.
Yeah, so you basically see why it works that way. And now let's assume that we have this function and we want to find the slope of a tangent line at some point. You say the point.
Let's say 1 and 3.
1, 3?
Yep.
It doesn't belongs to the curve. It doesn't belongs to the domain.
Oh wait.
Because 1 square is 1. You wanna find, let's find the curve at point 1, 1, okay?
Okay.
So let's assume we have point 1, 1. In this case, can you write me? Okay, I will write. We have point 1, 1. It's A. So x1 and x1 equals 1, y1 equals 1 correspondingly. How would the coordinates for xq look like? It's gonna look exactly like we said before. So xq is going to be equal 1 plus h, and yq is going to be equal this function, but when x taking value 1 plus h. You see it?
Yeah.
So the what we do here, when we substitute x to this value, we simply put it here. We can see that yq is going to be equal 1 plus h square, right? This is the x value. Do you see this?
Yeah.
This is our HQ value. After this step, let's simplify. Let's open this bracket. So what we're gonna get? You're gonna get a h square plus or minus? Plus 2h plus 1, right?
Yeah.
So now we have second point. Look, we have coordinate. This is exactly what we've been doing with the slopes, right? We have 1 point and second point. And we already know the formula for the slope of such a point. It's m equal to x2 minus x1. So the last point minus the previous one, right? And what? Oh, why aren't you telling me? What am I doing wrong? It's a raise over run.
Oh, so y2 subtract
It's
y1.
y2 minus y1 and the x2 minus x1. And we just simply substitute these values to what we know. We know that our x1 is 1 and our y1 is 1. But we know that our second point has these coordinates. 1 plus h and function with value of x equals to 1 plus h. You see?
Yeah.
So we substitute the values for h2, x2 and y2, and we're gonna get h square. This is where this is our y2. You see it? This is the y2 that we are using, and this is the x2 that we are using. So it's going to be x square, h square plus 2h plus 1 minus 1. This is the point that we are looking into. We are looking into tangent line in this point, in point A. And second is going to be 1 plus h minus 1, right? So we simplifying it. 1 minus 1 is 0. 1 minus 1 is 0. And we see that we have h square plus 2h divided by h, right? Can we simplify it?
Yeah, because
Yeah,
remove the h from the 2 and then the squared. So become h plus.
exactly. So we have h plus 2 at the end. But let's remember, how did we define the h? Can you tell me? What was this whole h idea about? This shift in x coordinates.
A very small number, so like 0.000.
Yeah, or we can simply say that it's so small that, that relatively to 2, we can assume it's equal 0 because we have a operation of sum, right? 2 plus almost nothing gonna still equal 2, right? So we're gonna rewrite this operation as limit for x equal 1, because this is the point that we are searching the tangent line in. You see? Limit for x equal 1, limit of m equals to the limit where h trying to reach zero. So h is not 0, but almost 0. We show it in this way. Basically, another way to show it is delta x traveling to 0. You see? These two different notations for the limit. Then we're gonna write h square plus 2h divided by h after simplifying everything, right? One more step, simplifying common factor, get h plus 2, and we see that h is traveling to 0, thus we assume that this is equal 0, and the answer is 2. So the slope of a line tangent to the parabola in point 1, 1 is equal to.
Okay.
Am I confusing you guys?
No.
No.
This is why I've been so slow with explaining you the basic stuff, because now we're going to use it, we're going to manipulate it to achieve real analysis. We're going to analyze some graphs using it, and this is the first step. So Yusuf, can you explain me what I did here to find the tangent, the slope of a tangent line of a parabola at this point? Can you briefly like tell me how would you do it now, the step by step?
To find the points?
To find the instantaneous, basically, instantaneous rate of change.
So I would use the rise over run formula, which is m equals y2 plus minus y1 and x2 minus x1.
Yeah.
And so I would plug in the numbers and just like solve it that way and like use the limits to figure out the
How
x
do you
and y points.
pick the value for point Q?
Point Q, so I would use the formula right there, which is plus HF at that one to just plug in the information I have and just solve it like algebraically.
Okay. So how would you write this formula in terms of letters, not 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 numbers, but letters?
Letters, so it would be Y, right?
No, for first part is that it's X coordinate always. First one is
Oh yeah, sorry.
always X.
So X plus H,
Yeah.
and then FY plus H.
No. This is one.
Yeah, so it would be Y.
So it would be X plus H.
Oh, sorry, yes, it's FX plus H, yeah, sorry.
So because this is what this bracket says,
Yeah.
it says this is the value of Y.
Value of
And
Y, yeah.
and Y is dependent. It depends on value of X.
Yeah,
And we finding value of Y in specific point by choosing this X value.
yeah.
So we can alternate only X directly. We can alternate it in such way that we can pick it greater for 1 or less for 2. It's up to us because it's a variable that we are operating with. It's like time. It's like, I don't know, what other variables do you know? There are, for example, variable, how many pancakes I eat per hour. That's
Yeah.
also a variable. So, Alan, you got this? Yusuf got it. Alan.
Yeah, I got it.
So what is A? Let's sum it up. What is A?
Our point.
The point that we are,
Just trying to find the instantaneous rate of change.
yeah. Because can you remind me what is the average rate of change?
Average is the secant line from the 2 points.
Yeah. So basically, it's average rate of change is equal to the slope between
2
two
points.
lines. So great. So let's save this for your reference. You're also gonna have a more clear explanation in the book. It's pretty much the same, but they're spending so much time onto finding these points that are close to the secant value, right?
Yeah.
Referring them to one another. They're using that to show you the idea. But if you understand the idea, there is no need to waste time on calculations like that. Okay. So, sorry, can you? Would you like to make a break or let's finish?
Let's finish.
You want to go forward, right?
Yeah.
So here, this is exactly what I've been showing you right now, but printed. You see, PQ is delta Y over delta X, and we write them down as we did. Can you see this? It's the same.
Yeah.
It's just another way of seeing it. So slope of a tangent as a limit. You can remember that the slope of a tangent line at a point, it's a limit function It's some limit function. Because there is no other way to represent it accurately. Because otherwise it's going to be approximation between two different values. We know that our value is somewhere in between. And this is the most efficient way to approximate it mathematically by using this limit. So here you can see it. This part is y2 and this part is y1. You see? Because y1 is the value of function with x1. And here they picked value for x equal a, or just some random coefficient. So let's move on. Here are some key ideas, note it down. It can help you to remember the algorithm of solving this limit function operations. Do you need a second to write it down?
Yes, please.
Take your time. So, are you confused why this limit stuff works? Or it seems logical to you?
No, it seems logical, yeah.
So great. It's pretty much like, you know, when you're not taking a very small fracture into account. You know, when you divide by the calculator, for example, for modular arithmetics, have you got it?
I don't.
No, not yet.
Okay, wherever. When you know when you cannot divide the the number is not divisible, and you're getting some fracture. And let's say we are asked to write down an answer in an integer. That's basically that's a scale of inaccuracy that we are given with. So for some application, accuracy must be within single unit. For the other application, accuracy must be up to some decimal places. And this accuracy varies from application. Here, we are studying the instantaneous value. So we basically we can break down the value as many times as we want. So up to the point when the result of the fracture, like this, when h is extremely small, when this fracture that we end up with is so small that it has no effect on the mathematical operation. It's like, imagine if I pour a bottle of water into the sea. Do you think the average sea level in the world is going to change?
No.
Most likely not, because it doesn't make any effect.
Yeah.
And here, our x, this a, is so much bigger than h, that h simply can be thrown away. But we can't throw it when we have a product. You see, here we're dividing by h, so we need to simplify it first.
Yeah.
Because if we will divide by h while approximating it with 0, we're gonna have a mathematical problem that you don't know how to solve yet.
Mhm.
So when you divide by 0, you see, that's why this h most usually is substituted in the final equation. If you're facing a problem that you have a 0 in the denominator, then it means there is no limit for this function in particular point. You got it?
Yep.
Yeah.
So let's say you have 0 on top, and that's okay, because your value for slope is going to equal 0 if you have some number on the bottom, right? If you have something here, and you're dividing 0 by it, you're gonna have a slope equals 0. What is slope equal 0? Can you tell me? It's horizontal line.
Yeah.
It's basically a horizontal line. But if you got a 0 in the denominator, you're getting a value and you have some value on top, it's going to be infinity, basically. If you
Yeah.
divide something into by 0, it means that you divide something by very small value, basically 0, 0, 0, 1, and even farther. And you can see that product of such operation is going to equal infinity. But sorry for throwing this into you. You're gonna learn how to deal with this type of equation when there is no limit. You're going to approximate the function using another functions, just as we did it here with seconds, right? Basically, what seconds are in this graph? What seconds?
The slope from point to point.
Not just slope, it's approximation of this function in this range.
Mhm.
So in this value of y, this line acts almost like initial graph. You see? And the closer this line to the graph, the more accurate the approximation. The smaller the difference here, you see? Across the graph, we can see the difference between the value for the seconds and the value of the graph. And the smaller this difference, the more accurate the approximation. Because you can approximate it like this, joining the beginning of the coordinate system, 0, 0, with the end of this graph. And it's still going to be approximation, right? Because the starting point and the end point are same. It means that the function are somehow similar, right? But it would be less accurate approximation than the one where we approach this point so close to one another, so they create a perfect tangent line. So let's go ahead and solve some examples. Determine the slope of a line perpendicular to each of the following. Can you remind me the definition of the perpendicular line? Two perpendicular lines. What the property they share?
Lines that make a 90-degree angle when they intersect.
Okay. And what else?
Um,
I'm gonna give you a hint. It's something related to M and B values. Maybe not B, just M.
they're too linear.
So the product of their slopes, M1 times M2, is gonna equal 1. Or is gonna equal -1. Just give me a second. Let me recall something. Sorry, guys. So yeah, it should be equal -1. Basically, what we can take from here, that if we know M1, we can represent M2 as -1 divided by M1, right? And this would be the value for the perpendicular line to what we are looking at, because this is the line, you see. And we can say what M is equal to right away, right? In this case, M is equal 3, because M is a coefficient in front of X. And B, what B is equal to?
The y-intercept.
Yeah, B is equal y-intercept, exactly. And it's in this case, it's equal -5, right? So when X equals 0, Y would equal
To -5.
-5, yeah. So we know M, we already know M based on just what we know about linear equation. So perpendicular line would be -1 divided by 3. This would be the slope of the perpendicular line.
Hmm.
The reason why you need this, because later on you're gonna learn about products of vectors, and perpendicular vectors, parallel vectors, they share some properties when you make an operation with them. That's why this is why we're touching it. Just remember this ratio, that M1 times M2 equals -1 when they're perpendicular. But if you know this one, you can substitute secant value from this if you want to, right? It's not that hard. Here's to find the slope of any line perpendicular to this one, we take the negative reciprocal of it.
Uh-huh.
Did you write it down?
Yeah.
Perfect. And let's take a look at the second example. Here, first of all, we would represent this equation for y, right? We're gonna move everything that is contains no y to the right. It would be -13x plus 11, right? Divided by -7. We can get rid of this minus by simply changing the signs, or the other way. Do you know how? Taking minus out from the brackets in here. So it was plus in the brackets. Now we change it for minus. You see? You're familiar with this one, right? How do we simplify the equation?
Did you move all the other terms to the you moved 13x to the left and then 11 to the left?
So I took 13x to the right,
Yeah.
11 to the right, and then I divided the right side by -7.
Yeah.
Or you can do it the other way around. You can move
I would
it would be preferable. You would move -7y to the right, and it would be equal to 13x minus 11 equals 7y. You see, I got exactly the same result, but a bit different way.
Yeah, fine.
So can you tell me what would be the slope of this line right away?
13 divided by 7 x equals, yeah, that's cm.
Remember, this is the slope value of the slope already.
Subtract 11 and then the b is 11 divided by 7.
Yeah, 11 divided by 7 here. And now we just need to find the reciprocal of 13 divided by 7. And it's pretty much simple. It would be equal to 1 divided by 13 divided by 7, right? And we just flip it. But we're gonna flip 13 divided by 7, and there is a minus in front of it. So it's going to be -7 divided by 13. And this would be a angle. This would be the slope of the perpendicular line. You got it, Yusuf?
Yeah, I got it.
This is pretty much how do we link the formula of a line in this case to some practical application. We know M, we know some properties of two lines when they're perpendicular, you see? So, would you like to solve something harder?
Yeah.
Would you like to practice sketching graph?
Oh. Sure.
Okay, so before doing that, let's talk about rate of change a little bit, and then we're gonna end our class with few practical questions, okay? So rate of change. Remember, I've been trying to explain you about differential equation, and I showed you that differentiation of formula for path gives us formula for velocity. You remember?
Not really.
Yeah, I don't remember that either.
So today you're gonna see what I was talking about. Basically, what is rate of change? Can you explain me in a simple words? Rate of change is basically a speed that defines how something changing, how quickly something changing, right? This is what can the tangent line to a curve give us. For example, if we're talking about a formula that describes speed, you see, we have describes distance. So we have distance by time, right? Let's say formula looks something like this. It would mean that we went straight forward, then returned back, then turn around, something like that, right? And if we take tangent line, for example, in this point, slope of this line, basically rate of change would be the slope of this line, right? And here we can see that the rate of change would be equal to 0, right? Because it's horizontal. The slope of this line would be equal to 0, right? It's top point of this peak, this hill. Can you see that?
Yeah.
And what it means in an example with speed, with distance. If we're moving forward and then we're moving backwards, it means somewhere in between we stopped, right?
Uh-huh.
It means that on this top point, the maximum of our function in this range, it means that here our speed was equal to 0. So our instantaneous rate of change in this point is equal to 0. Do you see what I mean?
Yep.
It means that our speed at this period of time was equal to 0. And here, because it's logical, before going backward, after going forward, we need to stop. And this extremum, that's how it's called in math, extremum of this function. Extremum, it's basically a position where function changes direction from growing to decreasing, for an instance. So here you can see example how rate of change can be represented. It's different. It's the ratio of the change to the change in time, for example, delta S by delta T. And this is exactly what we know, delta Y by delta X, right? Exactly the same, just different coordinates. So basically, once you learn how to measure instantaneous rate of change, basically you learn how to measure a slope of a tangent line on a curve. Once you did that, now you can tell what was the rate of change at a particular point of the time or in a particular point of the graph. For example, if you were asked to, like, this is the graphic of the distance covered by me while I was traveling on a bike. This is how the distance I covered changed over the time. Can you tell me what was my speed? So instantaneous rate of change, like 10 minutes before the end of my ride. What was the instantaneous rate of change? Or in other words, velocity. What was my velocity at that time, right? How fast I was going at that point of time.
You could. Do you want us to solve it?
There's nothing to solve here. Here is the example that he says he covered 340 kilometers in 4 hours. This is what I was showing you last week. I divided the overall covered number of heartbeats by the time that these heartbeats were made during. So for example, I divided 50 heartbeats that were made from 0 second to 30. So value on the bottom is delta x. When the first point is 0 and the second one is 30, you write delta x equals 30 minus 0, right? You see what I mean, guys?
Yeah.
Basically here, he says he was writing for 4 hours. So he's writing 4 on the bottom here because 4 minus 0 is equals 4. Because 0 is the starting point, it's x1. Did you already know this before today's class?
It's this all of the stuff.
Yeah, about instantaneous rate of change.
Yeah.
Just
Okay.
a little bit, not too much.
So here are some more formulas that you can write down for yourself. Instantaneous velocity. It's a limit function. It's instantaneous rate of change, as we discovered previously. Average rate of change is the difference between 2 points, and instantaneous rate of change is the limit in the specific point. Limit when we are approaching difference between x1 and x2 to minimum, to 0. So let's solve some tasks practicing. Do you still need some time to write it down?
I got it.
Yeah, I got it too.
Perfect. Let's solve some oh, sorry. Can you still see my screen?
Yeah.
Perfect. I would like to test you. No, I would like to test myself if I'm a good teacher, if you understood anything at all. Let's work with this graph a little bit for the understanding. Between which two consequent points is the average rate of change in the function the greatest? So let's do it verbally without calculation or something. We have these 2 points, we have these 2 points, we have these 2 points. So between which two consequent points is the average rate of change in the function the greatest?
A to B.
HAB, yeah.
Yeah, because the incline angle is the biggest one.
Yeah.
And here we can say that the angle is even negative.
Yeah.
So function decreasing. Is the average rate of change in the function between A and B greater than or less the instantaneous rate of change at B?
Greater.
Greater, yeah.
It looks like it's greater, right?
Yeah.
And I can say that it's greater because here you can see how the graph is basically rocketing up, right?
Yep.
It's rocketing up. And here we can see that it starts slowing down. It's basically not growing as quick for over you can measure it by this period. You see, this is basically delta y. This is delta y, and this is delta x. And if you compare these values, you can see that this one is definitely not as fast. Sketch a tangent to the graph somewhere between points D and E, such that the slope of the tangent is the same as the average rate of change in the function between B and C. Oh my gosh, did you understand it? Sketch a tangent to the graph somewhere between points D and E. Okay, tangent to a graph. Where should I, at the lowest point or somewhere here? Tell me. 1, 2, or 3.
I don't understand the question.
It says sketch a tangent to the graph somewhere between points D and E. Let's do it. Somewhere between these points. So we have
Oh, yeah.
domain that defined by,
Let's do bottom.
let's do in the bottom. Okay. In the bottom is going to be horizontal, such that the slope of the tangent is the same as the average rate of change in the function between B and C. And
But
between B and C, you can see that we picked up the right line right away.
yeah.
Because here between B and C is basically what would we get on the top or on the very bottom.
Mhm.
And it's pretty cool that you already know this property now, because now you can it's like searching for a vertex of a parabola, right?
Yeah.
You say that the equation is equal to 0, etc.
Mhm.
So a construction worker drops a bolt while working on a high-rise building 320 meters above the ground. After t seconds, the bolt has fallen a distance of s meters, where st, this is the function.
Mhm.
So let's do it. Calculate the average velocity during the first, third, and 8th second. So I would strongly recommend you, when you're working with this type of questions, please write down your points right away. It's gonna save you some time later, maybe. So here we've been asked to calculate the average velocity during the first, third, and 8th seconds.
Okay.
First, so x is basically equals t, right? X equal 1, 3, and 8.
Mhm.
So calculate the average velocity during the first, third, and 8th seconds. How would we measure the average velocity?
Would it be so? Would it be?
So average velocity, it would be velocity in a range from 0 to t,
Yeah. So it'd be
and
0.
from t, in this case, the first. Here, you see, one of them is the first, second one would be was the third second, and the third one would be between 0 and 8th second. So all these points connected together would be an average velocity during this period of time.
So would it be? It would be 320 meters over 1 subtract 0,
So
or is it?
just give me a second. I'm gonna show you step by step how we can do it.
Or is it?
So first of all, what we need to do, we need to know 2 points, right? We know first point. What is the first point? The beginning of the run, 0. It must be 0, 0. So it would be 0, 320. While x equals 0, the height is 320 meters.
Mhm.
At the starting point of time, he dropping the bolt from the very highest point, right? So now we know the first point. Let's find the second point. X equals 1. We can add it here. It's going to be 320 minus 5, right? 315 then. You see what I mean?
Yeah.
So in the same way, what would be the second point when x is equal to 3? Nine times 5, how much is it?
Um.
It's 45.
So subtract 320 subtract 45. 275.
Yeah, and the final one, 8 by 8, it's 64. 5 by 64 is 320. So 0.
Yeah.
So it means after 8 seconds, the bolt drops down. And this is what we see here. The formula, initial formula is given to us where t in the range from 0 to 8. And when would this range stop? When the bolt hits the ground, right? When the fall of the bolt stops. So how would you plot this graph for me? We know that this must be parabola, right?
You could just do 1, 3, and 8 on the bottom.
So yeah, you would plot the points exactly. You would plot the point 0 first, x equals 0, y equals 320, or s equals 320. It would start here, then second point would be somewhere here. You see, we're still slowly increasing the speed. We're slowly changing. Now in point 3, somewhere here, it's already gonna be far lower. And then point 8, let it be here. It would be 0. So our graph would look something like this, right? And sorry, I'm gonna try to make it beautiful. Okay, like this. One more time. Just schematic representation. And how would you represent this notation? I would separate the graph by 2 vertical lines because we know that t is in a range between 0 and 8. You see? And so it means we are studying our graph in this area, which is 0 to 8.
Yeah.
And this like line, it means something that we're not taking into account. So calculate the average velocity during the first, third, and 8th second. Now we know first and second point. The average velocity would be the slope between these 2 points, right? And we remember the formula. Do you?
Yeah.
So you can easily take these values, put them in here, and calculate the average velocity. What would you do in this interval from 3 to 8? In this, from 3 to 8.
You would same thing, fine. Just plug in the values from 3.
Yes, exactly. And to calculate the velocity at time t2,
Use a tangent line, and then you plug in your point 1 in the range, and then 1 the exact point, and the limits using the formula.
yeah, we're just simply gonna use the limits formula, and it's gonna look like this. Limit of m while h travels to 0 when h is this distance from P to Q. Our point P is going to be here, right? Right above the 2 seconds. So we're gonna have F 2 plus H minus F 2 and 2 plus H minus 2, right? So you would find the value for Y when x equals 2. And evaluate it by using this formula. Is this clear?
Yeah.
Okay. How do you feel, guys?
Pretty good. We're good.
So let's, what is the time right now? Let's solve some more interesting tasks, maybe. Something, because there are many tasks that require you just repeat the same process every time, right? We don't really want to spend time on that. Can you do this for me, guys? Just to fix knowledge, or it's too easy?
Right.
Just use the formula, right?
Oh yeah.
Let's not waste time on it. Here is some interesting tasks I found. Remember, this is about height and velocity, basically physical interpretation of what we studied here. A spaceship approaching touchdown on a distant planet has height h. In meters at time t, in seconds given by h. When does the spaceship land on the surface? With what speed does it land, assuming it descends vertically? So tell me, what would be the defining feature of this point when the spaceship finally lands?
Would it be 100?
No. What is the feature of this point? What would happen to the tangent line in this point?
It would
So when the ship lands, what happens to it?
From horizontal.
Let's say our spaceship lands horizontally, and this is the moment when he reaches the ground and something happens with our graph.
Mm-hmm.
So we know that h is going to decrease with t growing. When t is equal to 0, initial moment of time, it says that h is equal to 100, right? Then it's going to decrease like this, and it's gonna reach 0 somewhere, right?
Mm-hmm.
So we know that tangent line to the curve in this point is going to be horizontal to the time axis.
Mm-hmm.
So it's going to have 0 slope. That's the first thing that we can mention here. But the question is, when does the spaceship land on the surface? It's going to land on the surface when the slope and this point is equal 0, or h is equal 0, right? So we can simply solve this equation for h equals 0. But here is the second part. With what speed does it land?
Would the speed be land? Like the speed right before it touches the ground?
Yeah.
Oh.
So we can say about this speed, we can say that the velocity is going to be equal to instantaneous rate of change, right?
Mhm.
Right the moment before we land.
Mm-hmm.
And we're assuming it descends vertically. So even though the graph for height is like this, but the movement of the plane is strictly perpendicular to the ground.
Mm-hmm.
So we know that instantaneous rate of change on the graph is going to be equal this vertical component. So first thing, when does the spaceship land on the surface? We need to find the value of time when it lands. So let's say that the right hand side is equal to the left hand side and left hand side is equal 0. We're simply going to solve this equation, and last week I remember you showed some good methods like discriminant. First of all, what would you do in this case? I would simplify it definitely.
I would factor out 25.
Yep, so it's gonna be yeah, like that.
And then product sum.
So T1 would equal 2. So this is the product and this is minus sum.
So two and
So yep, so it's 2.
2 and 2, okay.
You can double check it, but we see that the solution is single, that it's going to reach the ground after 2 seconds. And you can see it here because this is going to be equal 100. This is going to be equal minus 200. And 100 minus 200 plus 100, yeah, 0.
I think it's -2 and -2.
-2?
Yeah, because the sum is -4. So it'd be -2.
No, sum. So x1 plus x2 equals -b. And in this case, b is -4. So -b would be equal 4. And x1 times x2
Right.
equals c.
Yeah, that's right. I did it. Forgot a step.
You see, remember there is minus here.
Mhm.
So now we found the moment when the spaceship reaches the ground. And Yusuf, with what speed does it land? How do we find the speed?
The speed, so assuming it lands vertically. I'm not sure how.
So you can find an average velocity from beginning to the end. And in this case, if you take a look, if it's equal 1, if t equals 1, we are going to be at 25 meters above the ground. So over the first second, we've been dropping down faster than after the first second, because from the first second to the second, we covered only 25 meters. You see? Does it make sense?
Yeah.
So if during the first second we covered 75 meters, and during the second interval of time we covered only 25 meters, it means that we are slowing down, we're decelerating.
Oh, so you'd find the secant line between that point.
So this question you can understand it in 2 ways. What is the average speed of deceleration, or descending, sorry, what's the average speed of descending, or what would be the speed in the moment of time when the
Yeah.
spaceship touches the ground.
Mhm.
And from this graph, we can say that by the moment the spaceship touches the ground, he decelerates his speed up to 0. So the moment when he touches the ground, his vertical speed is equal to 0. And this you would get if you take the instantaneous rate of change in point 2. You see? This is the answer that you would get by taking the instantaneous rate of change.
Mhm.
So can you show me how would we get 0 here? Answer 0.
Mm.
Yusuf, can you?
Check.
I'm gonna write down the formula.
Okay.
I'm gonna write down the formula. Just show me how would you use this formula. The formula is as follows. The instantaneous rate of change or instantaneous slope, particular point, is equal limit when h travels to 0, and formula for m for the slope is as follows. Our function in the second point, which is going to be x plus h
Yeah.
minus f x in the first point,
Yeah.
and below we have x plus h minus x. So in this case, if we want to know instantaneous rate of change in point 2,
Can I say something?
yeah, sure.
Would
I'm not so sure.
would it be
So Yusuf, do you remember what this x is in this formula?
Yeah, it's the
It's the
Uh,
point that we are approaching.
yeah, it's the one we're approaching. Yeah.
So just simply use this formula by knowing that the point that you're approaching is equal to 2. X equals 2.
Oh, so plug in for the x is the point we're approaching. So it'd be 2.
Yes.
Oh, okay.
But plug in the value of x equals 2.
Yeah.
But for this, you see, for this function, what value would you plug in for the first one? You would plug in value x plus h, right?
is h 0 or is it very close to 0? So 0.01.
You're not substituting h for any value at this point. You just leave it as h, and at the end you can say that h is equivalent to 0. So we are not taking h, we're not actually taking some value of h here.
Okay.
And to find the value of y in this point, x plus h, you're simply substituting your variable in the equation to what you have here in the brackets, x plus h. In our case, it's t plus h.
Then
Time plus some difference.
would you
So rewrite, okay, you know what is fx means?
yeah, I know what the fx means. So would it be I'm just trying to find out what you would put for the f.
For the f, look, f it means function.
Yeah.
Fx means y. If we say fx plus h, we say that this is some other value of y in this point where x is equal to this value of x plus some h. So if you represent the points on the graph here, and we're looking into this point, this is
Okay. I think I got it.
this is our point.
So
So function fx plus h would be equal to f2 plus h.
Yeah, can we also do this thing, It's, so. Oh, h equals. Is the h in the beginning of the equation also equal to fx? Or does h?
Can you point it out? Can you point it out?
Says right here, this h,
Yeah.
but then would it be, what if you plug it in?
So sorry guys, maybe I misleading you. This h has nothing to do with this h.
Yeah, yeah, I
Yeah.
got it.
Yeah.
It would be,
You understand it, right? It's two
Yeah.
different variables.
it would be 25, and then it would be x plus h squared, subtract 100 x plus h plus 100,
Yes, exactly.
subtract 25 x squared, subtract 100x plus 100 divided by the equation again. Oh no, divided by h, sorry. Or x plus h, subtract x. What
Yeah,
is it?
take a look right here. I'm writing it down for you. Yusuf, did you get this?
I'm writing it 1 second.
So this would be the value for our function in some point.
It's all over h, right?
No, not yet. It's gonna be later when we put it into the function for the slope.
Oh,
Right now we want to,
it's you have to subtract it by the equation again.
yeah,
Because,
so by 25, we can subtract it by 25.
oh yeah, simplifying it.
You see, we simplified it. And now we are going to expand it. This is a square of a sum. It's easy. This is just a product. 4t plus 4h plus 4. Now let's look into what we can substitute here. Can we simplify anything? Not really. So let's write it down as it is. I'm gonna clear up some room on top. Keep looking. So now we know value for y2, right? It's going to be ft plus h and this value. Now we're going to write the limit function for h traveling to 0. First one, we're writing this one, this second point, because it's difference delta y. Let me write it like this, delta y over delta x. Or in our case, you see, we have h and t. So it would be delta h over delta t. Isn't it? It's not confusing for you? And we're gonna change this variable h to x0, okay? Let's call it x0, t0. So next step, we are writing y2 or h2. Again, it doesn't matter, it's just the coordinate axis, you see? Delta h is equal to t square plus 2th plus h square minus 4t plus 4h plus 4. minus value of function in what point? In this point, right?
Yeah.
0.2. So it's it minus 0. And now we finally divide it by difference of x, and difference of these two x's is going to be h. You see? Now, what we do, first of all, we need to subtract this h somehow. We're gonna see that maybe it wasn't the best idea to expand it, or was it? T plus h. Can you see the way how we can simplify it? Can we group it up?
Well, what if we took the first equation and then just subtracted it by the equation again? And then we put it all over x plus h, subtract h, and then canceled out the terms. And then plugged in our h value and then our x value, which is 2.
So T, we're gonna plug in. Oh yeah, guys, this is what I missed. That's why it doesn't work. Sorry, guys, because T is equal to 2, right? This is the point that we are looking into. Now we can substitute T for 2, and everything is going to fold perfectly.
Mhm.
You see it?
Mhm.
T is only equal to 4, T squared plus 4h plus h squared minus 8 plus 4h plus 4 divided by h. Now, this t 4h plus h squared. Now we see we can simplify it. Minus 8 plus 4 plus 4. Now we have, this is something random.
You could cancel out the h's.
Now we have 4h plus h squared. Actually 8h, because you see 4h plus 4h. So 8h plus h squared divided by h. And if we put it out of the bracket, we have 8 plus h. And remember, it's a limit function. So h travels to 0.
Yeah.
So we can see that instantaneous speed, it's not actually 0 in this point. We assumed that it would descend its speed completely, but in fact we can measure that it had some speed before stopping.
So it'd be 8 meters per second.
If we were talking about meters, yeah, meters and seconds.
Mhm.
So his speed was 8 meters per second.
Okay. That makes sense.
You see, I made a mistake because I assumed that it stops perfectly here. But you see, your parabola that you're building like this, it can be sharp, it can be smooth, you see? It can vary. So guys, can you tell me, have you got an idea about instantaneous rate of change now and how math is related?
Yeah, kind of, yeah.
So now, final thing that I want to ask you. You see here we worked with distance, but in terms of height. Would anything change if we are not talking about the height, but instead of height, we're talking about vertical distance, like how far somebody away from me? Does it make change? Does it make change?
No.
So it's still going to be some distance. And here we can see that by finding the tangent line at a point, we know the velocity. And another cool thing that I'm gonna show you right now is that velocity can be found by like a derivative from this equation. And we're gonna take first derivative of this one. We're gonna find the speed, the equation for speed for v, and it would look like 50 times t minus 100. And this would be an equation for the velocity. If you put some values in here, then you approximate it, or you measure instantaneous value in some point, you're gonna see that the value is going to correspond with one another. But this is about differentiation. This is another mathematical tool that you also can use to find speed from distance. You can find acceleration from speed. And we're going to take a look into it, but step by step, because the discrimination, differentiation, there's discrimination, differentiation, they all are based on limit functions. When we are studying attitude of a function around specific point. So guys, do you have any questions about today's class?
No.
Before we finish, I would like to ask you, it's really hard for me to judge what type of material would you like to listen, whether it's more of a lecture or more of a practice, because I don't know your background.
I prefer practice.
You prefer practice, right?
Yeah.
What about you, Yusuf?
I prefer a lecture more.
So anyway, I'm going to fulfill both of those duties during our classes, but you remember you said that you're looking for good grades at school, right?
Yeah.
So I have a following suggestion. You see, most of this theoretical material is intuitively understandable. I don't know, did you struggle with this limit?
No.
No.
If you spend like half an hour practicing assignment, you're gonna catch it up. But we spend much more trying to explain it to one another verbally, right?
Yeah.
Instead of this, we can spend more time on solving practical questions that you may face at school or later on anywhere. We can just keep focusing on practicing. You can give me your exercises from the same topic that you are struggling with, and I can tell you how to solve them. So we can dedicate more time to practicing. Okay. You like it more?
Yeah, that sounds good.
So how you'll like if I'm gonna give you some reading material, you read it prior to our meeting, then we meet, I ask you a question about theoretical part that you were supposed to cover. If you don't understand anything or if you don't know, I go over it again. And then we do the calculations, practicing.
Yep.
Okay, yeah, that sounds good.
Because you see here, all you need to know to solve these tasks, it's on this page. This is equations you gotta remember by heart. Then you have some advices here and there. Here you can see the representation of the same stuff. There is no need to cover it together all over and over again. I would prefer if you can read it on your own. But still, I'm going to talk about it. I'm going to talk about it a lot, but in this way we can be more precise about what you understand and what you don't, instead of me pushing all the information all at a time at you.
That's good.
Okay, okay, guys. So today I'm going to add this lecture to the Google Drive. I'm gonna send you Google Drive link again, and I'm gonna post a hard copy of a book where you can take exercises for yourself for next class. I'm gonna also add a Word file with the numbers that I would like you to solve by the next class.
Okay.
Perfect, guys. Thank you. Thank you for your attention. I hope you enjoyed this class, and I'm looking forward to see you on Thursdays.
Thank you so much. Have a good day.
Good luck.